So now that we've introduced the notion of what an antiderivative is, and we've upgraded our bestest friend sheet to inform us of some handy antiderivative or indefinite integral formulas, let's take a look at those in the process of examining some examples. So real quick, just start things off here. Make sure I get this guy right. So we have the indefinite integral of this particular polynomial that we want to find. 3x to the 4th minus 9x cubed plus 7x minus 6. Now, in the past, I've sort of laboriously broken these things down using properties in the interest of conserving space and time. I'm not going to do that. I'm just going to say we can deal with each one of these individually and then combine the results together, via the sum and difference formulas that appear on a reference sheet. So I will take a moment, though, and write out sort of the constants out front of these guys. By the time it's all said and done, we'll probably just lump them together. But the 3 kind of comes along for the ride as we find an indefinite integral or antiderivative for x to the 4th. Our power rule tells us that would be 1/5 x to the 5th minus 9 coming from that next term. Again, we call in that, reverse power rule for x cubed. We go up to x to the 4th. We've got to divide by 4 plus 7. Our exponent here is a 1, even though we don't usually write it. So using the power rule there, 1 plus 1 is 2. Divide by the new exponent of 2. This last guy is a little bit tricky because he's not explicitly called out on the formula. You could look at it as 6 times x to the 0 and then use the power rule on that. If you do, that's fine. What I usually just end up looking at is saying, well, what's a function whose derivative is just negative 6? Well, negative 6x does the job. Now, this is an antiderivative. It's not the indefinite integral in this case because I've left something off. That's right, I didn't write that constant of integration at the end. I don't have the plus c. So I will do that here in the next line. I'm also going to collect together the numbers floating around in front of each term. So we have 9/4 x to the 4th, 7/2 x squared minus 6x. Then we have that plus c hovering around in the back. So that's one example down. So let me label that, because I'm going to try to sneak another one in here right underneath it. So polynomials, hopefully it seems pretty reasonable how the guys like this will behave. The next guy I want to take a look at may be a little bit trickier to handle. So and smile last. So this time around, I'm going to need to do a little more maneuvering before I can actually start invoking the rules from our bestest friend sheet. So I have the cube root of x to the 4th plus the 4th root of x cubed, and then I've got 1 over x to the 7th hovering around in the back. The catch is, rules for those guys don't immediately appear on the sheet if you take a look. What I'm going to need to do instead is do a little bit of algebra. This is the kind of maneuver we've been doing a lot over the course of the semester, so hopefully this feels appropriate. I can take this guy and write it as an exponent that happens to be a fraction. So in this instance, I'd have x to the 4/3 plus the cube root of x to the 4th would become x to the 3/4 power, and this x to the 7th living in the bottom of a fraction would be x to the negative 7th. So I still haven't done any calculus yet. This is just the algebra to get things in place where I can. So I'm a little cramped for space. I'm going to try. No, I don't trust myself. So, sorry, you got to leave. Okay. So, moving on up here. Now I can use that same power rule on each one of these 3 terms. So 4/3 plus 1 would give me x to the 7/3, and then I need to divide by that new exponent. So 1 over 7/3, we'd normally write that as its reciprocal, 3/7. Same deal is going to happen here. 3/4 plus 1, 7/4. Flip that over to represent the division up front, and we'd have 4/7, x to the 7/4. Here, when I add 1 to my exponent, negative 7 plus 1, that's right, it doesn't get more negative, goes back towards 0. We have x to the negative 6. You'll notice I haven't filled in the plus yet because when I divide by this new exponent, I'm dividing by negative 6. So I'm going to write that as minus 1/6 x to the negative 6th power. And I've already spoiled it, so I won't act suspenseful. We need that constant of integration at the end. We need the plus c. Done. So what if we have things that aren't necessarily power functions? We haven't messed around with any of those rules yet. Everything's been a power function. Let's take a look at one. So we have, I'm also going to throw things at you by using the variable theta this time around. So we've got 8 sine of theta plus 2 cosine of theta minus 3 cosecant squared of theta, and I'm going to fit my d theta right in there at the edge. Sorry, he's a little squished, but yeah, d theta. You can write that on your own paper much more clearly than I have right there. Again, step by step, I can break this down, work out each antiderivative separately, then put them together. Just like with that first example with the polynomial, these constants essentially just come along for the ride. So we'll have 8. Looking at our bestest friend sheet, the antiderivative of sine of theta is, beat, negative cosine of theta. So I normally, instead of writing a minus right here, I put the negative out front. We talked about that with derivatives. If you put it right there, make sure you're using some sort of brackets or parentheses so you remember that it's a multiplication and not 8 minus, like a subtraction of the cosine function. So here, we have the plus 2 antiderivative formula for cosine of theta, gives us sine of theta. And as usual, make sure you're writing the of theta. We don't. This isn't a theology class. We're not talking about sin or just cos or anything like that here. So lastly, minus 3 cosecant squared of theta. That one's a little more obscure, but if you take a look at the bestest friend sheet, we have the minus 3. The cosecant squared antiderivative is negative cotangent of theta. So I have cotangent of theta, negative of negative 3 is going to be a plus 3. And don't forget that constant of integration at the end. So negative 8 cosine of theta plus 2 sine of theta plus 3 cotangent of theta plus c. I'm highly confident I can fit this next example in. So he's using some of my favorite stuff here. So we have 5e to the x minus 10 over x. And we want the indefinite integral of this thing. So the exponential function e to the x should be one of our favorites. Hopefully you'll recall the derivative of e to the x is e to the x again. As it turns out, its antiderivative will then be e to the x again. So as usual, the constant just kind of comes along for the ride. So we have 5e to the x right there. 10 over x is maybe a little bit trickier. I'll go ahead and write the minus 10 because, like we said, constants come along for free. 1 over x is the same thing as x to the negative 1st power. So if you look, the very second rule on the sheet, right underneath the power rule that we used when we were dealing with stuff like this, says what to do in that case when you have x to the minus 1st, because trying to use that power rule would force you to divide by 0. We've talked about nobody wanting to go to math jail, so don't do that. Instead, if you have x to the minus 1st, your antiderivative is the natural log of the absolute value of x. It's easy to overlook those absolute value bars, but don't, because this thing technically allows for the possibility that either x is positive or negative. Nothing here is barring that from happening. If you don't include the absolute value bars, you can't handle negative x values. The natural log function is not defined for those for our purposes. So 5e to the x minus 10 ln absolute value of x. Again, plus c, close off the box, we done. Okay, so there's some examples of how we can use these antiderivative formulas from our new and improved best as friend sheet to calculate antiderivatives of various functions. There are a couple of extra wrinkles I want to toss in, but I think it's a good time to press the pause button, and then we'll pick up with those tricks in another video.